In this lesson, we will introduce several differentiation rules and interpret derivative as rate of change. Let's begin with some basic rules. Let's assume C is a constant, N is a rational number, F, G, they are differentiable functions. Constant rule says derivative of a constant is equal to 0. Well, this should make sense because geometrically speaking, let's take a look at what a constant looks like. So a constant function is a horizontal line, right? Y equals C. And derivative is the slope of tangent, and because it's horizontal, at any point, the slope of tangent the tangent line coincides with this line, so therefore the slope is also 0. Using from the definition perspective, we can see that the derivative, the definition is the limit delta x approaching 0, f of x plus delta minus f of x over delta, right? Delta x. So this is the derivative of f. Now this time the function is a constant. F of x is equal to c for any value of x. Therefore, the derivative will be f of x plus delta will be equal to c, and f of x will be also equal to c, and this is equal to limit delta x approaches 0, 0 over delta x, which is 0. Therefore, this limit is equal to 0. The second rule is power rule, and we have a power function x to the n, where this n is a rational number. It doesn't have to be integer. It can be a fraction. This rule says the derivative of x to the n is equal to n times x to the n minus 1. The exponent is 1 less than the n in the derivative. I'm going to skip the proof of this rule, but we'll be using this rule quite often. The next rule is the constant multiple rule. This rule says the derivative of a constant times a function is equal to this constant times the derivative of this function. In other words, this c, constant c, can be factored out or can be pulled out from this derivative. This rule, well, let's quickly look at how we can prove that, because it's always good exercise to prove some result that helps you better understand the definition. So now, in this case, this is actually our function, right? This is the function. C times f of x is the function. So using the definition, we should evaluate this function at x plus delta x. So therefore, the function should be c times f of x plus delta x minus this function evaluated at x. So this function at x, which is c times f of x divided by delta x. We can see that in the numerator, we can factor out a c, and because of this is a limit, we can continue to factor out the c outside the limit sign. So therefore, we have c times the limit delta x approaching 0, f of x plus delta x minus f of x. I'm running out of the room here, over delta x. And this is exactly the f prime, right? This is the definition of f prime. So therefore, this the derivative of c times f is equal to c times the f prime. That is proved. The next rule is the sum and difference rule. This is saying the derivative of the sum of two functions equals the sum of the two derivatives. or the difference of the derivative of difference of these two functions equals the difference of the derivative of individual functions. So basically this is saying when you have plus or minus, you can distribute this derivative for each individual function. Now let's do some exercises. So the first one, find the derivative of the following. F of x is equal to 7. This is a constant. So the derivative, according to the first rule, it should be equal to 0, right? And the second one, f of x is equal to pi. Pi is a rational number, and it's still a constant. So therefore, the derivative of this function is still a 0. The next one is a power function, x to the power 6. Therefore, we use power rule. And in this case, the n is 6, right? So therefore, f prime of x equals, according to the rule, 6 times x to the degree should be 6 minus 1. So therefore, 6 times x to the power 5. And once you are familiar with the rule, actually quite often you can do this immediately without writing this intermediate step. Let's move on to the next question. The next one, 3 times square root of t. This is the function g of t. And from the rule, we can actually use the power rule. We can rewrite this square root of t as 3 times t to the power 1/2. Now, when we find the derivative of that, we are going to pull the constant out according to the constant multiple rule, pull the constant out or factor the constant out. So that this is, so g prime of t is actually equal to 3 times the derivative of this t to the 1/2, right? And therefore, we can use the power rule now for this part. So 3 times 1/2 t to the 1/2 minus 1, and which is equal to 3/2 t to the negative 1/2. In this example, very much alike to the previous example here, we can rewrite this into an exponent form and then apply both the constant multiple rule and the power rule. You may want to pause the video and give a try first. So here I'm going to have 1/2 is actually my constant, right? X to the negative 1/3 is the negative 1/3 is the exponent. Now y prime is equal to, we can factor out the constant and then find the derivative of x to the negative 1/3, which is 1/2 times, okay, power rule is used, negative 1/3 is the n, x to the, subtract the m by 1, and therefore we have negative 1/6 x to the negative 4/3 after the algebra. Okay, so we have practiced first 3 rules using these examples. Let's take a look at the next one, okay? So here I have a question for you guys. Here the function f of x is 10 to the power 6. Because I see a power, therefore I'm going to use the power rule. So let me know whether you think this is true or false. So the exponent is 6, so 6 times 10 to the, and then we subtract 1 from the 6, right, which is 10 to the power 5. So think about this, and you feel free to pause the video if you want more time to think about it. In fact, this is false. Why? Because this 10 to the power 6 is actually a constant, right? Constant. And the derivative of a constant should be equal to 0. For those people who are using the power rule on this function, I call that as abusing the mathematical rule. You just have to be careful. Now, next, let's take a look at the number 7. We have a polynomial here, and we are going to find the derivative. In this case, we are going to use the sum and difference rule right there. Basically, we just find the derivative of each individual term inside the parentheses here. So here we are going to find the derivative of x to the 8th, which is equal to 8 times x to the 8 minus 1, right? In the future, once you're familiar with this rule and then you feel comfortable, you should skip this step. Just quickly write that as x to the 7th. And the next term is plus 12 times 5 times x to the power. We have to decrease this power by 1. It's 5 minus 1, which is 4. And minus 4 times. And in the derivative of x to the 4th, power rule again. Exponent is 4. 4 times x to the power 4 minus 1, which is 3. And continue to the next term, plus 10 times 3 times x to the power 2, because we subtract this 3 by 1, right? Okay, now for this one, minus 6. So the derivative of x, the degree is 1, right? So when you find the derivative of this guy, 1 times x to the power 1 minus 1. And this is x to the power 0, it becomes 1. So therefore, the derivative of x is actually 1. So therefore, it's 6 times 1, okay? And the last term, derivative of 5, which is a constant, it's going to be 0. Therefore, I'm not gonna bother to write it now. After that, we should simplify. So therefore, this is equal to 8 times x to the 7 plus 60x to the 4th minus 16x cubed plus 30x squared and minus 6. The next question is a rational function here. And some students might think, okay, let's find the derivative by finding the derivative of the numerator and denominator separately just as follows. So the derivative of the numerator, 2x squared, will be 2 times 2x, which is 4x. Derivative of x is just 1. We just did that. Derivative of negative 3 is 0, so we skip writing that. And derivative of x is the denominator here, which is x, is 1. Now, if you do that, actually this is incorrect. This is wrong. In fact, in the next lesson, we'll introduce a rule for quotients, which can be used to find derivative for any quotient. And now, in this particular case, even though we have not yet learned the new rule, we actually can solve this problem. We can still find the derivative of this problem because we can actually split this rational function into 3 separate terms. And the reason we can do that is the denominator is just a single term x, right? So therefore we can split it. So we're going to split so that the first term will be 2x squared over x, which is 2x. The second term will be x over x, which is 1. And the third term will be 3 over x. And this 3 over x can be considered as 3 times x to the negative 1. So with that, we can actually find the derivative using the rule that we just introduced. So the derivative of the first term, 2x, will be just 2 times the derivative of x, right? Which is 1, right? So 2 times 1. And plus the derivative of 1, which is constant, will be 0. And then the next term will be minus. What's the derivative of 3 times x to the negative 1? Let's apply the power rule. It will be 3 times the exponent, which is negative 1, x to the subtract 1 from the exponent. So now we have 2 plus 3 times x to the negative 2, which is 2 plus 3 over x squared. Of course, after we learn the quotient rule, we can use quotient rule on this function, but this actually is a little nicer, easier if you split it up into 3 terms. Next, let's take a look at the one of the application here. In this problem, we are given a function y equals x times square root of x, and 1 and 1, this is a point on this function, on the curve of this function, and we want to find the equation of the tangent line to this curve at this point. So in order for us to find the equation of a line, we need the slope, and we already have the point. So therefore, we just focus on the slope, right? And to find the derivative of this one, slope means we need to find the derivative. We can actually rewrite this as x times x to the 1/2, which can be combined as x to the power 3/2. So therefore, let's find the derivative of this function, which is x to the 3/2. The derivative is equal to 3/2 times x to the 3/2 minus 1, which is 3/2 times x to the 1/2. Now the slope, which is the derivative at x equals 1, is equal to 3/2 times 1 to the 1/2, which is 3/2. We have the slope, we have the point, therefore we can quickly find the equation of the tangent line at x equals 1, y equals 1 is, so y minus the y1, which is 1, equals the slope, which is 3/2, times x minus the x1, which is 1. And now let's do a little simplification. And we eventually have to add 1 to both sides to write that into the slope-intercept form. So it's going to be 3/2 x, and negative 3/2 plus 1 is negative 1/2. Okay, so this is the one equation of the tangent line at this point 1, 1. Now let's take a look at the second learning objective. We're going to find the derivative of some first two trigonometric functions. One is sine, the other one is cosine. So let's quickly walk through how to prove the first rule. The second rule is actually proved in a very similar way. We're going to just look at one. And to prove the first one, we actually need two special results from earlier section. The result is the limit x approaches 0, sine x over x. This is actually equal to 1. We proved this earlier. And the other one, very much related, is 1 minus cosine x over x equals 0. These are the two special limits that we can take advantage of when we prove the first result. And actually, there's another trigonometric identity that we will need to use. So sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha times sine beta. So this will be used to prove this one. If you want to do some exercise to prove that one, actually this is the identity that you will find useful. It's going to be cosine alpha plus beta is cosine of alpha, cosine beta minus sine alpha times sine beta. All right, let's prove the first one. So the derivative, the definition is limit delta x approaches 0 of the difference quotient, right? So it's going to be sine x plus delta x. This is the f of x plus delta x minus the sine x. This is my f of x divided by delta x. Now I have sine of the sum of these two items. We are going to use this identity there. So this is equal to limit delta x approaches 0 sine x cosine delta x plus cosine x sine delta x minus sine x over the delta x. I'll regroup those because we have two special theorems here, two special previous results. This one I want to have sine x and x paired together, and this is where I have these two paired together. Okay. The second one I want to come up with 1 minus cosine x, and for these two terms, we can factor out the sine x to create 1 minus cosine x. Actually, I want to factor out the first and third term, the negative sine x. So now let's regroup. This is going to be equal to, okay, this is my first term. So this is going to be cosine x sine delta x over delta x. This is my first term, okay? And the next one is actually these two. I'll factor out the negative sine x. So when I factor out negative sine x, I'm left with 1 minus cosine delta x. So when you factor out negative sine x, this term is we're left with 1. And this term is negative cosine delta x. All right, next we are going to split the limits, right? This limit actually gives you 1. And the limits of this quotient will give you the 0, so that this term disappears and we are only left with cosine x times the 1. So that's where we have the cosine x. So allow me not to save a little time, skip writing the limits of this term minus the limits of that term, and the limits of this term is going to be 0. Well, I strongly encourage you to give a try to prove this result using these facts, okay? And you can still use those results. Let's apply these two rules. By the way, this derivative of sine is cosine. Derivative of cosine is negative sine. There's a negative sign there. The derivative of the first problem, it's going to be derivative of y prime is the constant you factor it out. Derivative of sine is cosine x, right? Plus the derivative of x is equal to 1. And let's look at the second one again. Please pause the video and then do it yourself. Give a try first. And here comes my answer. So y prime is derivative of cosine is going to be negative sine x. Now, if you think for the second term, the derivative of the second term, if you believe it's 1/2 times cosine of pi over 3, then please reevaluate your answer. Actually, this is incorrect. And the reason is sine pi over 3 is a constant. So 1/2 times this constant is still a constant. So therefore, this is actually a constant. The derivative is 0. So therefore, this is the derivative of this function. Okay. Don't abuse the rule and then don't apply the rule to this one because this is constant. Don't apply this rule. Next learning objective, we'll use derivative to find rate of change. Derivative, it essentially means the rate of change of one variable with respect to another. Very often, we need to find the rate of change in different fields. For instance, if we want to find how fast a position is changing with respect to time, we need to find the derivative. How fast the population is growing with respect to time, we need to find the derivative, etc. Here, we'll look at one very classical area, which is the one-dimensional motion along a straight line. In such problem, we usually use either horizontal or vertical line to represent the straight line motion. On such lines, very often, movement to the right or upward is considered to be a positive direction. Movement to the left or downward is considered to be in a negative direction. Here's the detail. Suppose an object moves along a straight line and its location at time t is given by a so-called position function s of t. And the average velocity over a period of time, delta t, is given by the change in position divided by change in time. And change in position we also call displacement, which is displacement. And the derivative of the position function ds dt represents the velocity. This basically means how fast the position is changing or how fast the displacement is changing, the rate of change of displacement. Basically, velocity is the derivative of s, the position. Velocity can be negative, 0, or positive. When it is 0, that means it's stationary. When it is positive, say suppose you are using a horizontal line to represent the motion, straight line motion. If it's positive, then it's moving to the right. Okay, so when you're moving to the right, velocity is positive. When you're moving to the left, the velocity is negative. The speed is the magnitude of the velocity, which means speed is the absolute value of the velocity. Because of the absolute value, we only consider the magnitude. It cannot be negative. The instantaneous rate of change of velocity, that means how fast the velocity is changing. That's called acceleration. Because this is the rate of change of velocity, therefore it should be the derivative of the velocity. So therefore we are going to call acceleration, which is denoted by a of t, is the derivative of velocity. And because the velocity is the derivative of the position, right? So consequently, the acceleration will be derivative of the derivative of the position function, which is second derivative of the position function. This is actually a higher order derivative, and we actually will introduce in the next lesson. Wouldn't hurt to just mention it now. We actually call this as second order because it's second derivative. One thing is, be careful here. When acceleration is positive, is greater than 0, velocity is increasing. Keep in mind we only say velocity is increasing and not necessarily speed. For instance, if your velocity is changing in the following way, -5, and then -4, and then -3, -2, and so on and so forth, right? And then here the velocity, -5, -4, -3, -2, is actually increasing. You can see that so -5, -4, -3, -2, you can see it's increasing, the velocity is increasing. However, its velocity here is actually decreasing. This is faster and then going slower here. So we are just saying that acceleration is positive, velocity is increasing. Similarly, when acceleration is less than 0, the velocity actually is decreasing. When acceleration is 0, that means the rate of change of velocity is no change, no rate of change in velocity. That means velocity remains the same, which means velocity is constant. There's no change in velocity. When acceleration and velocity are the same sign, then the speed is actually increasing. So this is pretty important for you to determine whether the speed is increasing or decreasing. So again, look at the sign of acceleration and velocity. When they're the same sign, same direction, that means then your speed is actually picking up. When acceleration and velocity are of opposite signs, that means they are in different direction, then the speed will be decreasing. Now let's look at one application here. The position of a particle moving along a straight line is given by this position function, s of t equals t squared minus 4t, where t is in between 0 to 5, and t is measured in seconds, and the position is measured in meters. First of all, let's graph this position function. And to graph this, by the way, this is a quadratic function, right? So therefore you expect a parabola. And I can actually graph that quickly by just factoring the t out. And therefore I know t equals 0 and 4. These two are the zeros of this parabola. I'm going to mark that here, 0 and 4. Okay. And the vertex is definitely in between these two, so in the middle of the two, which is 2. So when t is equal to 2, so I have 2 squared, which is 4, minus 2 times 4, which is 8, 4 minus 8, which is -4. So therefore the vertex is 2, -4, which is right there. This is the vertex. And this opens up, and passing through these two x-intercepts, it should look like that. I'm going to just look at the range from 0 to 5. When t is 5, 5 times 5 minus 1, which is 5 times 1, so which is 5. So when t is 5, s is 5. So therefore the graph looks like this, right? Okay. Actually, we can, just by looking at this position function, we can talk about, we kind of have some idea of this motion. So suppose this particle is moving on this straight line, assuming when t is, when t is 0, so the position is 0, which means at the origin. And then when t is going from 0 to 2, let's take a look at the position function. Its position is going towards the negative, and then when t equals 2 is the far leftmost position, right? So which is -4. So basically it looks like this. From time to 0 to 2, right there, this is -4. This is time equals 2. This is when time equals 0. And from time 2 to 4, the position goes back to 0. That means the position changed back to 0, right? This is time equals 4. And from time t from 5 to 6, this 1 second, the position changes from 0 to 5. So therefore 0 to 5. This is when time equals 5. So basically the particle moves like this. First 2 seconds going to the left and far left. And then at that moment it turns back and travel to the right and stop at here, right? So basically go here and then go here. Let's find the average velocity over the time interval 0 to 5. The average velocity equals change in position over change in time, and which is s of 5 minus s of 0. The time change is 5 minus 0. And s of 5 is actually 5. We just plug the 5 in here, and then which is 5. S of 0 is equal to 0. So therefore, this actually is equal to 1 meter per second on average. The velocity is on this interval 0 to 5 is 1 meter per second. Next, let's find the velocity. So velocity is a function. It depends on the time. It is the derivative of the position function. And let's take a look at the derivative of this guy. So the derivative of t squared is 2t using the power rule, minus the derivative of 4t is minus 4 times the derivative of t, which is 1. So this is the velocity function. And when is the object stationary, which means at rest, and moving to the left, moving to the right, here we really have to look at the sign of the velocity, right? So when it's at rest, stationary, that means the velocity is equal to 0. The velocity is 2t minus 4. That's equal to 0. So this is when it's at rest. And which means t equals 2. Okay, so this is when the object is at rest. Now moving to the right, this is when this is greater than 0, which means t, we can set up the inequality like 2t minus 4 greater than 0, which means t greater than 2. And to the left, just simply set this velocity to less than 0, which means t less than 2, right? So that matches what we discussed earlier. From time 0 to 2, it's moving to the left. From 2, right at moment 2, it's actually turning. So therefore, at that moment, the velocity is 0. And then from this point on, greater than 2 to 5, that's to the right. Now, lastly, by the way, so 2t minus 4, if I graph that, when t is 0, it's negative 4. When t is 5, it's equal to 2 times 5 minus 4, which is 6. So therefore, this is the line. This is the line. And at the time 2, the velocity is 0. So this is the velocity function. And the blue one is the position function. Now let's find the acceleration, which is the derivative of the velocity. So acceleration is equal to the derivative of the velocity, which is derivative of 2t is equal to 2. Derivative of negative 4 is constant, which is 0. And now this is the acceleration. Is the particle speeding up or slowing down at time t equals 1? Let's check. At time equals 1, Let's check the velocity. Velocity when it is less than 2, which is in this case 1 is less than 2, we actually know this guy is to the left, right? So v of 1 is actually less than 0. You can check like 2 times 1 minus 4, which is equal to negative 2, less than 0. And but at this moment, a of 1 is equal to 2, which is greater than 0. We found that earlier. And because they are opposite sign, this is less than 0, this is greater than 0, it is slowing down at that moment, okay? Because of the, again, opposite signs. I think I should write down right there, opposite signs. Now at time equals 5, v of 5 is actually greater than 0, and a of 5, which is 2, is also greater than 0. It is speeding up. The reason? Because they have the same sign. All right, lastly, let's finish up this lesson by looking at another very classical example, the free fall object problem. The position of a free fall object, assuming that we are going to neglect air resistance, under the influence of gravity can be represented by this equation. You will actually learn how to derive this when you study the integral calculus. Where this s is the s0 is the initial height of the object, v0 is the initial velocity, this g is the gravitational constant on Earth. It is 32 feet per second, or 9.8 meters per second if we use the meter as the metric. Now, this problem says at time t equals 0 seconds, a diver jumps from a platform diving board that is 32 feet above the water. The initial velocity of the diver is 16 feet per second. So basically, assuming this is the diving board, and here's the water, and this diver initially jump upward and then dive down to the water. So with that information, we can actually find the position function. Here we are given the units in feet, so therefore we should use 32 here, right? So let's plug in 32. So plug in 32 here, and then the initial velocity is 16 feet per second. This is positive, that's why it's going upward at the beginning. So this is going to be 16. And this is the initial height, so we plug in 32 here as well. Okay, therefore the position function is -1/2 times 32, which is -16 t squared, plus 16t plus 32. Now, first question is, when does the diver hit the water? That means we are looking for the time so that the position is 0. That's on the ground level, which is 0. So that means we're going to set s to 0, find t, right? So this is what we're going to do. -16t squared plus 16t plus 32, we set to 0. And we can factor out the -16. We have t squared minus t minus 2 equals 0. And continue to factor. We have -16, t minus 2, t plus 1 equals 0, which means t equals 2 or t equals -1. Of course, because time is always non-negative, we're going to ignore this negative solution. So this is when the diver hits the water. What's the diver's velocity at impact? So we need to find the velocity function, which is the derivative of the position function. And so now let's find the derivative of this guy. So the derivative of t squared is 2t times -16. We have -32t plus derivative of 16t is equal to 16 times the derivative of t, which is 16, and derivative of 32 is 0. Now, when at time of impact, that means v of 2. So we plug in 2 for the t, and this is equal to -64 plus 16, which is -48, right, feet per second. All right, this concludes the lesson.